So I did finish the object-oriented solution to this. I was really slammed for finding any free time between last class meeting and this class meeting. I actually did quite a bit of thinking about it, including sitting there staring at the computer and looking at the grammar and thinking about it. But I didn't actually have time to sit down and do a lot of code writing until last night, and or I should say yesterday evening. And as a result, I didn't finish this thing till 4 in the morning, and then I woke up at 6:30. So the one thing I wanted to have prepared was a really smooth presentation to go with it, but needless to say, I'm feeling a little shaky with the caffeine, and don't have anything smooth to be planned. So I reserve the right. I think there will be parts that will go great, and it's possible that we're going to just drive into the ditch at some point. If that happens, I'll regroup, and on Tuesday I'll clean it up. But I'm hoping we get a good distance in explaining this approach. To start, I want to go to what I talk about with 111 students and talking about expressions in the language and how everything is just simply an expression. So we say int a equals 4 times 5 plus 6. Let me see, minus 2. And how I characterize the way this works to them is that the order of the precedence of operators is examined. So I normally come over to the web here and I type C++ precedence and bring up this good old-fashioned precedence chart, which is not coming. There it goes. And I note that there are 3 operators here. There's an assignment operator, a multiplication operator, an addition, or I guess 4, and a subtraction. And looking at this, you can tell that, and we all know this from grade school math, is that the multiplication and division happens before the addition and subtraction. And what's less, maybe intuitively obvious, but less explicitly so, is way down here is the assignment operator. So that's happening last. So the multiplication happens first. So as this is evaluated, first this part of the expression is evaluated. So that becomes a equals 20 plus 6 minus 2. And then the plus and the minus have higher precedence than the assignment operator. So those are the next two to occur. They do occur at the same level. Right here. And in that case, if they're happening at the same level, we evaluate them from left to right. So the next thing to be evaluated is the 20 plus 6. And then this expression is then evaluated. And then finally, this expression is evaluated. And that's what's left after the program is done evaluating the expression on line 8. Okay. We can make it a little more, let me just add one little feature in here, which is, let me create an int var equals 100. And I can stick in here var. Now this I don't do with the 111 students, but this is relevant to what we're doing in here, which is in evaluating this expression, what has to happen when, let's see, where do we end up going here? We have plus var here, plus var here, plus var here. All right, at this point, var needs to be evaluated. And when it's evaluated, we end up getting its value back. So that ends up being a equals 24 plus 100, and then a equals 124, and then we get a. Okay. So this is what ultimately that expression evaluates down to is a, and then there's no more evaluating to do, and so it then just goes to the next line of code. And maybe you're not aware of it, but this is actually a legal line of code. Let me see. I guess I should try compiling this. All right, so I have a warning that Mac compiler is doing that. I think if you did it on a Linux compiler, it wouldn't give you the warning. Neither here nor there. The point is that it did compile successfully into an executable there. So that's illegal. That's legal. All these are legal in the language, right? They're just expressions that get evaluated until there's no more to evaluate. Then it just moves to the next line of code. So taking that thought and returning back here, we did this a while back. If we look at this, these as objects, members, I should say, instantiations of classes, each of these are an object, I can have a member function called evaluate on this. And this would be, I'd call this an expression object, or maybe more specifically a plus object. And I tell the plus object, please evaluate. And what it has is that it's 2 pointers, so it goes to the left pointer, and it says evaluate. And then this, when it's asked to evaluate, looks at its 2 arguments, and it looks down on the left side and says evaluate. And this tells the constant to evaluate, and then it gets the 2 back. Now that it has the 2 back, it returns back up here, tells down here to evaluate, the 3 comes back. Now this has 2 constant numbers. It can do the multiplication, and then that returns back up here. So now this has a number on the left side, and it just comes down here, says evaluate, 4 comes up. Now this thing has 2 numbers, and it can go ahead and it knows how to add 2 numbers, right? So this is, I think, the key to developing an object-oriented approach to solving this parsing problem and dealing with these expressions, which we have to deal with so heavily in P5. The verbiage in the P5 description talks about don't cache any, it just happens, I'm right here, don't cache any values, only evaluate when you need to. So each of these expressions should only evaluate when they're told to. Now, that's fine. The question is, well, when is that top one told to? And if we look at so this is the, whoops, where do I have that open? So these things like this stuff, the math operator, the primary expression, all of this stuff ends up building this. It's creating, for instance, if I come like right here, right, this t plus, what this needs to do, we have it here as an expression. We're going to take, it's going to look slightly different here, but given this model, I would say that this would create a plus object. There's actually a plus class, and a plus class knows how to do addition of things. Basically, it tells the left side to evaluate, the right side to evaluate, then it's confident it has 2 constant values, and it can go ahead and add them. All right? So all of this stuff is just building that tree. Note that even when I put something, I'll end up doing something like this. There's no evaluation happening. We're just building, building, building. Right? What's $1? Well, that was a new statement to create a constant, or a new statement that created a multiplication or something like that down here. So all of this stuff ends up just building this expression tree, and in our grammar here, it doesn't get evaluated until, well, by golly, until we need the value. And where we need the value is right here. Again, this is all P4 stuff. This is my P4 solution. So this rule is where you have something like int x equals 23 times 4 divided by 8, right? Something like that. And this optional initializer, if we go back down, we end up hitting all those rules down below, where it's just simply creating more and more and more expression objects, creating this tree. So it's only at this point in time where you actually evaluate, whenever you need a value to assign to a variable. And so this is where we're going to find our commands to evaluate things. Now, let me draw a picture of what all of this would look like. That's going to be the best way to do this. Is that still readable? I don't know. Is that a yes? All right. I'll put this in. I don't want to talk about this right away, but I'll talk about it at some point. Oops. I'm actually going to emphasize these are classes, so I'm going to make that uppercase. That's done. Sorry, I didn't intend for this to be the Watch Todd Draw Hour. All right. Okay. Now there's inheritance relationships here. So inheritance plays a big part in this, and that's another drawback to this approach, although I believe it's quite graceful. It's going to be using some stuff that you probably haven't had a tremendous amount of practice using. One is a tremendous amount of inheritance, the other is virtual functions, and the other, whoops, that's not right, and also exception handling. So what I need is for you all to come to my 511 class where we deal with that stuff heavily. Okay, if you aren't familiar with inheritance diagrams, the derived class is pointing to the base class, and that's kind of follows the sentiment of visibility. If I have a base class, the base class has no idea of the derived classes that exist, but by definition when you create a derived class you say what the base class is, so the derived class is intimately familiar with the base class, so that's why you have the arrows going in that direction. Alright, so the one thing when we were looking at this diagram here that we were talking over and over and over again was this word evaluate. So expression here has a function. Let me ask a question first. When this plus sign asks this multiplication sign to evaluate, what is the plus sign expecting to have when it's done evaluating? When this is done evaluating, what should the plus sign have on the left side? A constant, absolutely. So I'm going to have to kind of extrude here. I'm going to go ahead and call this virtual. We'll talk more about the virtual functions if you're unfamiliar and for their significance here in a little bit. And so this is the function signature. Note that that this is one single hierarchy, right? Even though constant stuff is thrown over there to the right, everything that you see here is ultimately derived off of expression. That means every single class in this diagram has an evaluate function. So if you're a binary operator and you're asked to evaluate, you're going to ask both of your left side and your right side to evaluate, and then you're going to do whatever that operation is. If you're a unary operator, you're going to ask your operand to evaluate, and then you're going to do whatever that operation is. Here's a question. What if a constant has an evaluate function? What do you think the evaluate function for constant does? Let's actually try busting out a little code while we do this. So I have a class called constant. It's derived off of this expression class. Let's go ahead and start with that class. Let's put it all in the CPP file. Class expression, it has a virtual function that returns a constant pointer called evaluate. You're going to need a forward declaration because this is returned here and the compiler doesn't know what it is. So forward declaration to keep the compiler happy with line 3. Constant is derived off of expression. This is public. This up here doesn't do anything. That's just to say that the interface exists. If we look at this, what actually does the hard work is the plus, the divide, the tangent, the negate. Those are the things that actually do the evaluating, right? I just need to provide the interface to ensure that everything has the exact same interface. So what about a constant? What is there to evaluate? If a constant's asked to evaluate, and the objective is that whoever's looking at you and saying evaluate, you have to give them back a constant, what is the most obvious thing to give back? Right, or more generally, a constant, meaning yourself. So if you're a constant, so you can actually bust out the code for this right here. That's all that does. So now this chain, it doesn't matter. Actually, this is the picture. It's better to look at. The brilliant thing about this is you don't care what it is you're asking to evaluate. You just ask it to evaluate, and ultimately you have to hit these leaves down here where they're the constant object. They just return themselves, and then they start getting used in these operations, and you end up rolling up this way. Okay? So there's that. What do all of these binary operators have in common with regards to this picture? Every binary operator I can come up with, what do they all have in common? Huh? Two. Yeah, two expressions. So I guess I'm not writing so horrendous. I'm going to change this to blue and type expression, pointer, left-hand side, okay, so all the binary operators share those. Unary operators have just a single operand, so I just say expression, something like that. So now any of these that I create will have inherited those. So coming over here to the constants, we know that each of them have an evaluate that return this. What we need to do then with our constant is talk about the things that we do with constants. And what we do actually, let me avoid that so that I don't have to. All right, I'm going to implement these functions. If an integer what is the Wrong one. Where's my? Yeah. I'm going to throw one more out here. I'll throw out double constant. So again, this has an integer as data. Any huge guess as to what this has as data? Double, and string would have string, yeah? So if someone had an integer constant and they said, give me u in the form of an integer, then what is the line of code for that? Yeah, there's nothing complex about that. Here, same kind of thing. Now this will actually work as written because when you return an integer and it shows a double return type, it will go ahead and implicitly cast to a double. You can be explicit about it if you want. In fact, what I'll do is I'll put kind of the snooty pinky in the air C++ programmer way of doing it, which would be static cast double. All right, so that would be the hardcore C++ way of doing the cast. And then this, what is the function that lets us convert numbers to strings? Oh, actually, that's wrong. ToString. And I guess I can emphasize that that's part of the standard library. Pretty straightforward. What about the double? Here I can grab, actually what I'll grab is I'll grab lines 20 through 22. I'll yank them. I'll paste them right here. I'll delete those two, and then I don't need the casting. If I have a double and I'm asked to return it, I just return it. This is the same thing. There's a toString function that takes a double and converts it to a string. What about this one? What happens in GPL if I try to treat a double as an integer? Let me give you an example of a line of GPL code where I would treat a double as an integer, or I might ask. So I could have integer x, y, z. So there's an example of where when you're going through all the parsing and so forth, you get this thing. You aren't quite sure what it is, so you say, give me yourself as an integer. And that's an error, right? Okay, so here comes the next big piece of the puzzle, which is how do we treat errors? And traditionally, if you look at traditional functional programming, a function will return one value if it's valid and a different value if it's invalid. Well, there isn't any possible integer I could return which would indicate that it was invalid. So we need a totally different way of propagating errors. And that would be to use exception handling, where we throw exceptions. And what I'll do is this. And what is this part of? You actually see it over here in this GPL .y file, right? This is, where's my switch? The simple type, $1, and the simple type, if I hunt it down, it's right here. So that's where those are coming from. And we got all this stuff from gpltypes.h. Oops, I don't seem to have it. GPL singular. All right, the GPL type, so that's where that's coming from. So what I'm going to do is I'm going to throw an exception right here saying, you asked, basically saying, hey, I'm a double. That's all the exception is saying. And then for string, it'll be the same way, except for strings, it's impossible to, it's an error if you ask a string to be returned as an integer, and it's an error if you ask a string to be returned as a double, so both of those would throw string, and then this would be the only valid one for the string constant, which is to return itself. Okay? Now, I still haven't filled in the blanks as to the significance of throwing the exception, but we'll get there. I just want to establish that that's kind of how we're going to handle errors, is to just bail out and totally fly out of the function. All right. I want to, that comprises, I think, just about everything. Yeah, actually, in my completed P5, this is complete code right here. That's all there is to a constant. I want to ask a question. I'll do it anonymously to ensure I get good answers. Okay, so my question is, it's a pretty generic question, but I'm going to ask a second question. The next question I'll ask is, are you comfortable, meaning do you understand, are you groovy with virtual functions? I guess I'll ask 3 questions, because the third one I'll ask is exception handling. My guess is that I'll have the smallest positive feedback. So right now we are on this question right here. Multiple choice for all of these. A is yes and B is no. All right, it looks like twice as many of you are comfortable as not comfortable. Okay, I'm going to close that out. So then let's go ahead and go to this one. And then finally, exception handling. Well, there are a few of you. All right. All right. So I definitely oops. Let's see. I'm wondering if I can, if there's an exercise I can have you all do so that I don't have to simply lecture at it, because I know how boring it is to listen to lectures. All right. This is the I guess I should have asked about constructors, but that probably goes with classes. All right. So get that stuff entered in. I didn't write the stats function. You can go ahead and stick in some cout statements in there. I'm going to start this poll. Whenever you've finished what I've got up here, go ahead and just enter a choice so that I can kind of keep account of how many people have finished. And once I get at least half the class, I'll go ahead and move on. And once you've done that, go ahead and write a little simple main program to create a circle object and a triangle object. I'll do that myself once I'm able to scroll up a little bit. Give me a line number. It does, doesn't it? Thank you. So it should make mine work. All right. I know that about half of you are still plugging away on this. I'll try and keep it up as frequently as I can. I'm going to add one more function. If you're able to stick it in there, go ahead. I'm going to create a void setColor function. It's very much a gratuitous function. But what it does is it sets the color equal to the input parameter. And I'm just going to copy that, and I'm just going to paste it down here in triangle as well, so they're exactly the same in the two. So where inheritance comes about here, I'm going to go ahead and stop this poll here. The value of inheritance is in seeing different classes that share common elements. And there are three things in the idea, the process that you use is abstracting common elements up to a base class. Coming back, that actually fits very much with this, whoops, not that one, with this, where I went through a process. I started with everything you see down here at the bottom, and then I abstracted up things that were common. Now let me be very specific about what I mean by that when we look at this example here. There are three things. One is the data. Two are member function interfaces. What I mean by that is a member function interface. So let me say rules for abstraction. For abstracting stuff into a base class. 1, common data. 2, common member function interfaces. That is the function prototype declaration. That is let me bring it onto another line. The return type, function name, and number and type of input parameters. Okay. So, for instance, this function doesn't have anything in common with what you see in the other class. However, let's start with one here. Common data. We see that both classes have a piece of common data called color. So what I'm going to do is I'm going to create a base class. I'm going to call it shape. Let's create a shell for it here, and I'll put a public and I'll put a private. I noticed that I put private first. Let me just say that in industry it's standard to put public first instead of private. So I'll do that correctly here in shape. So what I do is I go ahead and I do number 1 is I abstract common data up into the base class. Now let me create the inheritance relationship. That's done by simply saying :public shape. And I do the exact same thing in triangle. Once I've done that, I can remove, this has been abstracted up, that color, so I'm removing it from the derived classes and I'm abstracting it up to the base class. Okay? If I create a circle, what you need to realize though is when I create a circle object, like on line 34, that object called disk has two pieces of information. It has a radius and it has a color. So even though I put that color being common up in the base class, when you actually instantiate the object, that object has all of the data in that derived class plus anything in the base classes. Okay? There are two separate things floating around. Disk is a circle with two pieces of data. A triangle is an what did I call it? The Transamerica building is a triangle with three pieces of data, the base, the height, and the color. All right. So I can't abstract base or height or radius because those aren't common between all my derived classes. Now I look at number 2, and I abstract up common member function interfaces. So we have two interfaces that actually are common, set color and stats. Set color and stats, those are common, so I'm going to put those two interfaces up here. Oops, I put that in the wrong area. It's void set color and void stats. So that's step 2. And then step 3, let me see, rules for abstracting. Common member function implementations. All right. So if 1 remove data from derived classes and insert into base class. If 2 and 3 are both common, this is worded poorly, let me see. Yeah, that's fine. If 2 and 3 are both common, remove the function from the derived classes and put in base class. So both 2 and 3 are true for our set color function, right? So the interface, they're both void. Where's my triangle one? So what I'm doing is I'm comparing lines 33 and 21. They both return void. They're both called set color. They both take character as an input parameter. And most importantly, the implementation is the same between both of them. So since they're identical, both the interface and the implementation, I completely remove them from the derived class and I put it into the base class. Now the third one's the tricky one. If 2 is common but 3 is different, put interface, maybe I'll use the word copy interface into base class and prepend with word virtual. So that's our stats. The interface for stats is the same. They're both functions that return void. They're both called stats. Neither of them take any input parameters. So I go ahead and copy the interface. That's what I did on line 13. And I prepend it with the word virtual. Now if you follow those 3 rules, you will never, ever, ever get inheritance wrong. We still have to look at the significance of why this is all a good thing, but when you do inheritance, do it this way. Look for common elements and abstract them up using these rules. All right, so now let's look at the advantage to doing that. Any questions to this point? Let me say that once you put the word virtual in the base class, it is not necessary, but it's customary to add it to the derived classes as well. The reason for that is if I look in triangle.h and I see void stats, if I see the word virtual there, I go, aha, it's a virtual function. And I wouldn't necessarily have that insight without looking back up into the file that contains the shape class. So it's a kind of a convenience for readability. But just to say, it's only required in the base class. The last thing I'm going to do, I'm going to add this prepend with the word virtual and append with equals 0. That makes it a pure virtual function. I will talk very briefly about it. I'm not going to go into detail. So this is only for the base class. For the equals 0. So note that there is no behavior, there is no function definition for stats in the base class shape. There's just the interface with the word virtual and the equals 0 at the end. All right. So let's come down here to our main. I'm going to spread out a little bit. And I'm going to create a shape pointer, shapely. And I'm going to say cout, choose a shape, 1 for circle, 2 for triangle. Int choice, cn choice, and then I'll say if choice equals 1, I'll put it all in one line, shapely equals new circle. I'm going to remove these lines down here, borrow. If choice equals 2, shapely equals new triangle with an R and a 20 and a 30. And now Anyone get that running successfully? So the key insight to this whole inheritance thing is if you end up having common, I guess what I should also do is, for the sake of doing it, do shapely arrow cout shapely get, or what was it, set color? Let me do it before. So shapely arrow set color, and I'll set that to X, and then here I will do shapely dot set color to Z. So what makes this approach to designing an application attractive is that when we write this program, we have no idea what shapely will be pointing to on lines 50 and 51. Could be a triangle, could be a circle. We don't know. We just tell it stats, and it'll do the right thing. If it's a triangle, it'll call triangle stats function. If it's a circle, it'll call circle stats function. Also, set color is the same for all of them. Remember, set color went entirely into the base class, so that behaves exactly the same way. So that is what makes, will be really attractive for that whole idea of that expression tree, because we just look at those expression objects and say, evaluate, and we don't have to know what they are. If it's plus, it'll do the plus thing, and if it's modulus, it'll do the modulus thing. So what I want to do is I want to go into a bit more detail on this. There's actually one more phase to this code here that I want to talk about on Tuesday, and then I'll continue looking at this hierarchy and how it's all laid out, and why it's a nice alternative to the other way. Because what I'll do is, before Tuesday, I'll take this example here and I will write up the equivalent example doing things the way they're done right now with that, with kind of the approach I had taken the other day, the original implementation. So with that, I'll cut you loose. Go ahead and look to the daily diatribe. I'll update this and make sure it compiles okay, and we'll just pick it right up on Tuesday.